Hello, welcome to CSC7913, Advanced Math for Computer Scientists. This is Brady Chen. This is part B of Module 9, Introduction to Number Theory. In first part of Module 9, Module 9a, we discussed about some of the basic concepts of number theory, the divisibility, and also the division algorithm. And then we talked about Euclidean algorithm that is used to calculate the greatest common divisor. Now, in Module 9b, we actually going to provide an overview of the concepts of modular arithmetical. So we're going to first provide the definitions for the modular arithmetical, and then we're going to explain the operations of extended Euclidean algorithm, which will be used in determining the primarity of a number. Okay, in Module 9a, we talked about the divisibility, right? So if we have two numbers, two integers, let's say n and a, and we say n divides a, if I can write a as the multiplication of n and another number, right? So then we can say n divides a. That means a is a multiple of n. So, but what about if n is unable to divide a? So that means a is not a multiple of n. So in that case, we can do the division and we can write a as, a quotient k times n, but a is not a multiple of n. So, we can find the k such that the a equals k times n plus another number r. Now, r is less than, greater than or equal to 0, and less than n. Now, why r is less than n? Because if r is greater than or equal to n, then we can actually, get another n and put the n in over here. So, for example, if we r is greater than n, then we can say a equals k times n and plus r minus n, because that one is still greater than n plus n. So then we can actually put this n into the combined n with the first term. Then we have a k plus 1 times n plus r minus n, and r minus n is still greater than 0, right? So we can make this one as the remainder. Now, if r minus n is less than n and greater than or equal to 0, and that's the remainder. So we can always make the remainder less than n. So if it's greater than n, then it's not a remainder. So we can continue to divide r into a fragment of, n. So we can always write a as the k times n plus r. R is a remainder. Now, here in this part, we're going to first define the modular operation. So if a is an integer and n is a positive integer, then we define a mod n to be the remainder when a is divided by n. Okay, so that says that a mod n is the remainder when a is divided by n. So in that case, when a is divided by n, now we got the remainder r. So then the modular modular operation actually returns the remainder when a is divided by n. Okay, now let's take a look at the example. So suppose a is 70, let's say 73, and n is, let's say 5. Okay, now what is a mod n? So this is the same as 73 mod 5, right? So let's see what's the result. So we're gonna actually do the division, 73 divided by 5. So then we can get the quotient 1. 1 times 5 is 5. 7 minus 5 is 2, 23. And now we have a 23. And then I can put the 4 here, 20. And then we got a 3, right? So we can get the quotient to 14 and the remainder 3. So 3 is the answer. And in the meantime, we can write 73 as the quotient times the divisor 5 plus the remainder 3. Okay, so that's the remainder. So the remainder is the result of modular operation. So this, in general, we can write, for any of a, if we a divided by n, so we can write a as, q times n plus r for some q. Now q is actually the division of a, is the division of a and n. So a divided n, but we keep the integer part, and we get rid of the fragment part. And the r is called remainder, which is less than n. So a can always write as, we sometimes call a floor division. So when you divide a by n, so the result may not be an integer. If it's a fragment, then we get rid of the numbers after the decimal point. And that's the floor division. We call it floor division. Okay. And then the second part is the remainder, which is defined as a mod b, or a mod n, right? A mod n is the remainder when a is divided by n. Okay, now here's another example. So 11 mod 7 is 4. Why? Because when we divide 11 by 7, so we got a quotient 1, and we got remainder 4. Minus 11 mod 7 is 3. Why is that? So now 11 can be written as 1 times 7 plus 4, right? And the minus 11 can be written as, let's say, minus 2 times 7, that's minus 14, and plus 4, or plus 3, right? So you can write as the quotient and times the divisor, which is 7, okay, and then the remainder 3. So that's the reason why minus 11 mod 7 is 3. So you can first write the a as the quotient times the divisor, and then plus the remainder. Then we can figure out what's the remainder and what's the quotient. Okay, so then we can always get the modular operation, the result for the modular operation. Okay, let's look at some more examples. So we got 4 problems, and what I'm going to do is I can actually pick the first one and the third one. Okay, so you can actually finish the remaining 2. So let's find 17 mod 9. So in order to do this, we can actually do the division, right? We can find, 17, 9. So we can do division and then put the 1 as a quotient. Then 17 minus 9, that's 8. Okay. So this is pretty simple. So we can write 17 as the 9, the divider, times the quotient plus the remainder. So the remainder is 8, right? So that's 8. Now we have a negative number. Okay. Now when you do the negative number, so we can first also do the division, regardless the sign. We have divide actually 140 by 23. So let's see what's the result. Let's see, 6, when I put a 6, 3 times 6, 18. Okay. So we got 2. So actually 140 is, 23 times the quotient is 6 plus 2. But now we're not looking at the negative 140, right? So it's a negative 140. So it's a negative 6 times 23 minus 2. But since the remainder should be a positive number, so what we can do is we can, here's negative 6 times 23, negative 2, we can put a plus 23 and negative 23. Now with negative 23 and the negative 6 times 23, we can put these together. We can get the negative 7, 23, and 23 plus 2, we got 21, right? So we can actually write negative 14 as the quotient of negative 7 times 23 plus 21, which is the positive number, which is less than 23. So the answer is 21 in this case. So for negative, so once you actually, you can start with the positive and do the division and create this, relationship. So then we put a negative here, and then we got a negative, the remainder becomes negative. So in order to make it, we can plus the number 23 and minus the number 23, and the minus number 23 combined with the first term. So we can actually, it becomes we can decrease the value of the quotient. Negative 6 becomes negative 7, and then the remainder becomes the 23 plus that remainder. So same thing we can do with the last one. We can first actually create this relationship. What is 370 divided by 17? So it's a 17 times a quotient plus the remainder, which is positive. And then we put the negative 17, which is equals negative question mark 17 plus minus, and then we can actually plus 17 minus 17 and combine this minus 17 with this one, and then we add these two, and this becomes the positive number. So I leave that for you. So we talked about modular operation. So that A mod B basically means when A is divided by B, and we got the remainder. So that's the remainder. Now, with the modular arithmetic, we can actually define the relationship between two integers. That's the first thing we're going to define is called a congruent modular n. Okay. Now, two integers, A and B, are said to be congruent modulo n, then if A mod B equals B mod A mod n, equals B mod n. And then we say A and B are congruent. Now, if A and B are congruent, we can actually rewrite this relationship with this term. We say A equals B mod n. So then that means A and B are congruent mod n. Don't forget mod n. Okay. So when it's possible that the A and B are congruent mod n, but A and B are not congruent mod t, another number. Okay. So this is important. Now, based on this definition, we will see that if A is congruent with 0 mod n, then we know that n divides A. Now, why is that? We can easily actually figure it out. Okay. Now, what does A congruent n mod n? This basically means A mod n equals 0 mod n, right? By the definition of congruent. Now 0 mod n, what is the value? If 0 mod n, so that means it's a remainder when 0 is divided by n. Now what is this? It's 0, right? When 0 is divided by any number, the remainder is 0. Okay. Or in another word, 0 mod n is the remainder, right? So we can write 0 as n times some number plus the remainder, right? Now, you can easily see 0 equals 0 times n plus 0. So the quotient is 0 and remainder is 0. So it's 0. So that means A mod n equals 0. Now, what does that mean? So that means when A is divided by n, the remainder is 0. So that means A equals n times k plus 0, right? So that means A equals k times n. What does that mean? That's a definition of divides, right? So if I can write A equals k times n, that means n divides A, because A is a multiple of n. So now here are two examples. So we say 73 is congruent to 4 modulo 23. Why is that? Because we can easily see that when I divided 73 by 23, so then what's the quotient for this case? I put a 3, so it's 3 times 23, that's 3, 3, 9, 23, 60. And then 73 divided by minus 69, that's 4, right? Okay, so 73 mod 23 is 4, right? Because 73 divided by 23, the remainder is 4. So that's by definition of mod operation. Now, what is this 4? 4 is actually the 4 mod 23. Okay, so 73 mod 23 equals 4 mod 23. Then that's basically means 73 is congruent with 4 mod 23. Now, similarly, we can actually do this. So 21 mod 10, what is this? It's 1. Minus 9 mod 10, we can easily figure out that's 1 as well. So 21 mod 10 equals minus 9 mod 10. So that means 29 and minus 9 are congruent. Okay, are congruent. Mod 10. Don't forget the mod 10. To congruent modulo 10. Okay. Now here are some more properties of modulo arithmeticus. Okay. So property number 1, A mod n plus B mod n and the whole thing mod n equals A plus B mod n. So that means A plus B mod n is the same. I can, if I want to actually evaluate A plus B mod n, I can first evaluate A mod n and evaluate B mod n, and then I add these two and then mod n. And also A mod n minus B mod n, then the whole thing mod n equals A minus B mod n. Also, that applies for the multiplication. A mod n times B mod n, and then mod n again equals A times B mod n. Now, what's the significance of these properties? Now, you will realize that these are very, very important, properties. We'll see why. Okay. Now, so to prove this, it's relatively simple. Let's actually check, prove the first one. Let's demonstrate the first property. Okay. So now let's say, let's actually assume that the A mod n equals Ra. Okay. B mod n is Rb. So then we know that that's the remainder when A is divided by n, right? So that's Ra because that's the definition for the mod operation. And that means, when B divided by n, then the remainder is Rb. So I can write A as J times n plus Ra. So that's the remainder. The J is supposed to be the quotient when A is divided by n. Okay. And then we can write the same for B. B equals Rb plus Kn. So that means when B is divided by n, I got a quotient A and a remainder B, and the remainder B is the result of B mod n, right? For sin kb and for integer k and integer j. Now, once we define this, then we're going to say, we're going to start from A plus B mod n. So A plus B mod n is the same as I substitute A with Ra plus Jn based on this. And the substitute B with Rb plus Kn. Okay. So then we can combine Ra plus Rb, Ra plus Rb, and then we can combine Jn and Kn, and then we take the common factor out, right? So it becomes K plus J or J plus K times n mod n. Now you will see that this is the same as Ra plus Rb mod n. Why? Because K plus J times n mod n is 0, right? Why it's 0? Because when you divide, K plus J times n by n, then you will get a quotient of K plus J, but you got a remainder 0. So that's 0, right? So the second one they're going to disappear. Now, what is Ra? Ra is A mod n. Rb is B mod n. So now we say A plus B mod n equals A mod n plus B mod n and mod n. Now, we can do the similar things for subtraction, for multiplication. Now, just keep that in mind. These three properties are so important. It's very, very important. It's basically the foundation for the modern network security. Okay. Okay, let's take a look at some of the examples. So now we can actually use example. The first example basically means when we actually calculate the 11 mod 8, and we got 3, right? And 15 mod 8, we got a 7. We can easily verify. Okay. Then we actually can verify that the 11 mod 8 plus 15 mod 8 and then the whole thing mod 8, right? Now what is this? So 11 mod 8 is 3, right? Mod 8. 11 mod 8 is 3, as we discussed here. And 15 mod 8 is 7, right? That's 7. So then we have mod 8, right? So we replace this by 3, replace this by 7. So we have it's 3 plus 7 mod 8. And then we have 10 mod 8. Now what is this? This is 2. Okay. Now if we can directly calculate 11 plus 15, instead of 11 mod 8 plus 15 mod 8, we can directly calculate 11 plus 15 mod 8. Now what is this? That's 26 mod 8. Now what's the result? Again, 23 or 26 divided by 8, we got a 4. Oh no, I'm sorry, it's 3. 3 times 8 is 24, and we got a 2, right? So it's 2. So we got the same result. That's expected because that's the property of the modulo addition. Okay. So this is 2, and this is also 2. And the same thing. 11 mod 8 minus 15 mod 8. Okay. And then the multiplication. Now, you can actually check that this one has a very important, this one is very important because sometimes when you try to actually calculate 11 times 15 mod 8, then we need to do the multiplication first, right? And then we got the result, and then mod 8, and then we got result. Now, if we can do this, if you say 11 mod times 15 mod 8, if we can actually do the 11 mod 8 first, 15 mod 8 first, and then we can actually get, 3, right? 11 mod 8 is 3. And then 15 mod 8, we get to 7. So now the 11 times 15 becomes 3 times 7 mod 8, which is 21 mod 8. Now we got the same result. Okay. That's very significant. Because imagine if we try to actually multiply two numbers, A times B. A is pretty big. B is a big number. And then you're going to actually multiply two big number, right? You got the result, and then you do the modular operation, say mod n. Now, instead of doing this, why we just say, can we actually do A mod n first? And then do B mod n. Now, what's the value of doing this? Because if A is bigger, very big, n is relatively small, A mod n should be smaller than n, right? Because A mod n is when A is divided by n, and we got the remainder, right? B mod n is the remainder when B is divided by n. So both A mod n and B mod n should be smaller than n. And hopefully it's much smaller, much smaller than A and B. So then you're going to do the smaller multiplication, A mod n times B mod n. And these two numbers are smaller than A and B. And then we do the modulo n, right? Now, if you don't know this, let's think about this one. So let's suppose that we try to calculate this. Multiply mod, let's say phi, mod phi. Think about this. Okay. Now, if we actually directly calculate this, we need to actually do the multiplication between two numbers, huge numbers. Now, what about if I do 19396 mod n, mod phi first, and then 36176 mod n. So we can do the division. We divide, actually, we get the remainder when I actually divide 19,396 by 5, and we got a remainder. The remainder should be somewhere between 0 and 4, right? And then we divide actually 36,176 by 5, and we got a remainder, right? These two remainders are very small. And then this division is relatively small, right? Think about this, okay? And then we can actually, once we got this number, and then we multiply these two numbers, right? We multiply these two numbers, and then do the modify. Okay. This is going to save a lot of calculations for us. Okay. Okay, let's check some more example, and we try to illustrate why these properties are so important and very significant. So first example, we try to use the properties of the modular arithmetic to calculate the following. First one, 12,562 times 23,789, and then the result is actually modular with 13. Okay, now if we don't use the property, we have to do the multiplication of two big number, right? And then get the result and do the modular operation. Now, with the property, what can we do? So we can actually do the, 12,562 mod 13 first, right? And then times 23789 mod 13, right? And then the whole thing just mod 13. Now, what is the first one? To calculate 12,562 mod 13, we need to divide 12,562 by 13 and get the remainder, right? So we can do this. 13. Now, what's the result? So we can actually put the 9 here, and we got 3 times 9, 7, yeah, 117. Then we do the subtraction. We got 8, 125 minus 117, 8, 86. And then we put the 6. So we got what we got? 86 minus 72. That's also 8. 72. And then we can put the 6 again, and we got 78. So 82 minus 78, that's 4. So that's the remainder, right? So then the first one, this one, the remainder is 4 times the second one. So then we divide 2, 3, 7, 8, 9 by 13. Then what we got? So let's see. We got a 1, 13, 0, 1, 107. Then what do you get? We can put an 8 here, right? So when we put the 8, 38, okay. Then we can put the 2, 26, 2, 1, 120, and then we just, put the down 9. So we have a 129 here. Now for 13, what we need to put? So we need to put a 9. So 9, 3, 7, 3 times 9, just 7, 2, 1, 1. So we got 2, 1. So we got the remainder 12. The quotient is 1829. That's the quotient. The remainder is 12. Okay. So then we got this, and then modular 13. So 4 times 12, we got 48 mod 13, right? What is the result? 48 mod 13. So we got 3, 48 minus, we got 9. Okay. So the result is 9. Okay. Now in this case, instead of doing a multiplication of 2 huge numbers, we actually do the modular for each of the smaller number, and then we just multiply 2 small numbers and the modular 13, then we got a result. This is going to dramatically save our time. And also, later on, when we actually use the computer program, we will find out it can also dramatically save the memory space, because we don't need to store a huge number before we actually do the mod operation. Now the second one, it's kind of tricky. It's a 234 square mod 13. Now square is actually this. You can write square as 234 times 234, right? Mod 13. So, and then you can apply the mod operation for each number. So it's a 234 mod 13 times 234 mod 13, right? And then we have a mod 13. Now what's 234 mod 13? Let's check. We need to get the remainder when 234 divided by 13. 234 divided by 13, right? So we got put the 1, 13. So we have 104. Then what do we put? We can put the 8. 3 times 4, 3 times 8, 24. We carry 2 to the next position. 1 times 8 plus 2, 10. Huh. 234 divided by 13, we got remainder 0. So this is 0. Times, this is the same, right? 0. Mod 13. What's the result? 0, right? It's pretty simple. So in this problem, we save a lot of time because we don't have to calculate 234 square. Because once we calculate, it's going to take a lot of time. And then with the result, mod 13, we eventually get 0. So this is good. Now, we can actually extend the concept of the power to a general case. For example, so instead of like if we say a to the k, so that what is a to the k? So that means you multiply a k times. So a to the k is a times a times a times a. You actually multiply k times, right? Mod n. Now, if a is bigger than n, then we can actually, do a mod n first, okay? And then put the power k and then mod n. Now, what's the advantage of this? Because a mod n should be smaller than n, which mostly should be smaller than a. Okay, definitely smaller than a, right? So this is going to save a lot of work. So this property is very interesting. So you, instead of actually do the power a to the k, multiply a k times, and then we actually do the modulo first, a mod n, and then multiply a mod n k times. Now, we know that by definition, the modulo n operator maps all integers into the set of integers we call the Zn. Now, Zn is a set of all the integers from 0 to n minus 1. Now, for example, Z8 is a set of integers from 0, 1, 2, 3, 4, 5, 6, 7, which is actually 1 less than 8. Why? Because when you actually do the modular operation, like a mod n, then we basically get the remainder when a is divided by n. So the remainder should be smaller than n. So if we talk about if n is 8, when any number is divided by 8, then the remainder is always smaller than 8. Now, the remainder is actually the modular operation, right? So a mod 8 is actually the remainder when a is divided by 8. So of course, the result should be smaller than 8. Okay, so we basically define the set called Zn. Now in this case, Zn is 8, right? Now this gives us a suggestion that can we perform arithmetic operation within the confines of this set? Now in another word, so let's say, just take an example of Z8, okay? We just forget about general Zn, it's basically the same. So let's say if X is an element in Z8 and Y is an element in Z8, can we define the operation like a plus, minus, multiplication within this set? So that means if X is actually belongs to Z8, Y belongs to Z8, can we define the X plus Y modulo 8? So we can make sure that the result is still in Z8, right? So we can define the, modulo 8, plus modulo 8, minus modulo 8, multiplication modulo 8. So make sure the result is still within Z8. So X minus Y modulo 8. Hopefully it's still in 8. X times y modulo 8, and which is still actually within Z8. So that means all these operations under the modulo 8 is actually confined in these Z8. So let's see, take a look at the example. Say we pick a number like a 6, and we pick a number x equals 6, and we pick a number y pick as 5. So then 6 plus 5 mod 8. What is this? 6 plus 5 is 11 mod 8. So we got 3, right? And 6 times 8, 5 mod 8, which is 30 mod 8. And then we got mod 8. 30 mod 8, it's 2, right? Oh, I'm sorry. Let's see. 30 mod 8. 3 times 8, 24. So we got a 6. So it's 6. So if x6 and 5 are the element of Z8, 6 is the element of Z8, y5 is the element of Z8, and the result with modulo 8 operation for the multiplication is still actually in Z8, right? So we can actually define the operations that with all these operations, now the result is still in these set. Okay. Now in previous slide we define a set called Zn, and in this particular case we call Z8, which is defined as a set of integers from 0 to 7, right? 0, 1, 2, 3, 4, 5, 6, 7. Okay, and then we try to define the arithmetical modulo 8 operation that so within based on this operation, so any elements in these 8, any 2 elements, when you actually play the operations, then the result is still in that set. Now first we define the plus operation, okay, for Z8. So now, so if 0 plus 0 modulo 8, we know it's 0, right? And the 1 plus 0, 1 plus 0 modulo 8, we got a 1. Now we can pick a random number, say, let's say 7 plus 6 modulo 8. What's the result? The result is going to be located in the intersection of these, in the cross, we draw the horizontal line along the 7, we draw the vertical line along the 6, and we find out the value is 5. So that means 7 plus 6 mod 8 is 5. Now we highlight certain of the special number 0 here. Okay. So that means if I add 3 and 5, 3 and 5, modulo 8. So 3 plus 5 is 8. Modulo 8, it's 0, because when 8 divided by 8, the remainder is 0, right? So it's 0. So that means 3 plus 5 modulo 8 is 0. Now, these pairs of numbers are very special. Now we have a couple of pairs, 6 and 2, right? 6 and 2, we got 0. And then we can say 2 and 6, and 4 and 4. These are a special pair. And then we would define like something called inverse, additive inverse. So that means 3 is an additive inverse of 5, because 3 plus 5 modulo 8 is 0. Now, this is actually generalization of the inverse. Okay, what does inverse, additive inverse means? So if we have a number A, what's the additive inverse? it's a number x such that the x plus a is 0. Then that's the additive inverse. Sometimes we use minus a to represent this. But this, with the arithmetic actual operation in Z8, the inverse is also going to be in Z8. Okay. Now here's the multiplication within Z8. So let's pick any numbers, like 5 times 6. So 5 times 6 modulo 8. And then 5 times 6 is 30. 30 modulo 8 is 6. Okay. So, and then we pick another one, 7, 2. 7 times 2, that's 14. 14 modulo 6 is 6 as well. Okay. So that's the table for multiplication modulo 8. Now again, in this case, we actually pay a special attention to the numbers. So when they multiply these two numbers under modulo 8, the result is 1. We pick some of these. Okay. So for example, 3 times 3. Okay, 3 times 3 modulo 8, which is actually 9 modulo 8, which is 1. Now in this case, we call the multiplicative inverse of 3 is 3. Remember that in general math, when we say, okay, say x, x times a is 1, then we say x is the inverse of 1. Okay, it's a multiplicative inverse of 1. But in this case, we have a modular operation. So the multiplicative inverse of modular operation can be also defined in a similar way, right? But there's one big difference between the general multiplicative inverse and the multiplicative inverse and the modular sense. So we will talk about this a little bit later. So you can see that the multiplicative inverse of 1 is 1 under modulo 8. Multiplicative inverse of 5 is 5 under multiplicative modular operation. Looks like it's the same, right? So 7 is the inverse of 7 and the multiplicative modulo 8. Okay. So we mentioned the additive inverse and the multiplicative inverse in the previous slides in the table for Z8. Now, let's actually compare the difference between the additive inverse and the multiplicative inverse in a general sense and then in the sense of a modular operation. Okay. So let's say if I have a number 8, now the multiplicative inverse of 8 is the number x such that the x plus 8 is 0. Now this gives us result that what is the value of x? X is minus 8, right? So basically the additive inverse of 8 is minus 8 because 8 plus minus 8 is 0. That's always the case. Now what is the additive inverse of minus 3? Then it's 3 because additive inverse of minus 3 is minus 3, and when you have minus and a minus, then so minus and a minus 3, it's actually 3, right? So that means the additive, x is 3. So x is additive inverse of minus 3. 3 is the additive inverse of minus 3. Now for multiplicative inverse, for any numbers, it's a number such that the a times x is 1. Let's say if I have 3, a is a 3. Now what's the number that when they multiply by a, it's 1. So x is 1 over 3, right? Because a times x, 3 times 1 over 3, we can cancel out, then that's 1, right? So that's why sometimes the multiplicative inverse x for a number a is sometimes called the reciprocal of a, because it's, the reciprocal of the number. So in general, if a is not 0, then the inverse of a is 1 over a. So sometimes we also use the notation a to the minus 1 to represent the multiplicative inverse of a. So that's very important. If a is 0, then there's no multiplicative inverse. Okay, only when a is non-zero, then the multiplicative inverse of a is the reciprocal of a. It's 1 over a. Now let's compare the additive and multiplicative inverse modulo n and the modulo sense. Now let's define the additive inverse modulo n. Now let's see the difference in the definition. The additive inverse x modulo n of an integer a in Zn. Remember the Zn, it's a set of integers from 0 to n minus 1. Okay. Now, the additive inverse x modulo n of an integer a, which is in Zn, is the integer x, also belongs to Zn, such that the a plus x modulo n is 0. Or, like a plus x and 0 are congruent modulo n. Now see the difference. Okay, x has to be in the Zn as well. Okay, so what does that mean? This means if I say, let's say Z8, okay, now 3 is an element of Z8, right? So what is the inverse of 3? Remember, in general, the inverse in general sense, the inverse is minus 3, right? Because 3 plus minus 3 is 0. But because we have to make sure the elements are confined in Z8, so minus 3 is not an element of Z8. So you cannot say minus 3 is the inverse modulo n. Okay? So we have to find the element in Z8 such that the 3 plus the element is 0 modulo n. So that's the reason why we say, what's the inverse of 3 modulo n? It's 3 plus 5 mod 8. That's 0, right? 3 plus 5 is 8. 8 mod 8 is 0. So that means 5 is the inverse of 5 is the inverse modulo 8 of 3. Okay, 5 is the inverse mod 8 of 3. So you can go back to check the table for Z8. Now, for multiplicative inverse modulo n, it's even more complicated than the multiplicative inverse in the regular sense. Remember, when we talk about a, like a equals 3, the multiplicative inverse is the reciprocal of a, right? So a inverse is 1/3. Now, this is definitely not going to work, because if a is an integer, a inverse is not even an integer. It's a fractional number. Now, in our definition of a multiplicative inverse modulo n, a multiplicative inverse for a number a, we still use the same notation, a to the minus 1 is a number x which belongs to Zn such that a times a modulo n is 1. So that means x should be also an element in Zn, which is also an integer, right? Zn is actually an integer, a set of integers, which is from 0 to n minus 1. So in this case, the inverse of a is not even a fractional number. It's also an integer. So that's completely different from the inverse, multiplicative inverse in the regular sense. Got this? So that's the reason why if we talk about Z8, so now what is the inverse of 3 modulo 8? It is 3 and the modulo 8. Why? Because 3 times 3 mod 8 is 9, mod 8 is 1. So 3 times 3 mod 8 is 1. So that means 3 is the inverse of 3 mod 8. Okay, so and also you will realize that not every element in Z8 has a multiplicative inverse. Not. Okay, so if you check the table, we will find out many of the numbers in Z8 has no multiplicative inverse. Okay, so let's take a look at this table. Okay, it's a table 2.2c. Okay, I got 2.2c. That's so it's an additive and a multiplicative inverse modulo 8. So that table is also for the elements in Z8 because we are talking about the numbers 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7. So we talk about 0 to 7, right? So what is the additive inverse? So every element in Z8 has an additive inverse. So 0 is the inverse of 0, modulo 8. 7 is the inverse of 1, modulo 8, because 1 plus 7, modulo 8 is 0, right? And the 6 is the additive inverse of 2, modulo 8, because 2 plus 6, modulo 8. So as far as two numbers add together, you got 8, then they are actually inverse to each other. Okay, so these are the additive inverse for each of the elements on the left. Now what about the multiplicative inverse? We use for every number w, we use w to the minus 1. So then 0 has no multiplicative inverse. That makes sense, right? Even in the general sense, 0 has no reciprocal. There's nothing like a 1 over 0. What is 1 over 0? It doesn't make any sense. Now, 1 is the multiplicative inverse of 1 modulo 8. Now, for number 2, there is no multiplicative inverse modulo 8 because I can't find x in Z8 such that 2 times x modulo 8 is 1. Okay, so that's why the 2 has no multiplicative inverse modulo 8. Don't forget the modulo. Okay, now 3 has an inverse. Okay, the inverse is actually itself. 3 is the multiplicative inverse of 3 modulo 8. Now 4 has no multiplicative inverse modulo 8. 6 has no multiplicative inverse of modulo 8. Now 5 is the multiplicative inverse of 5 modulo 8. 7 is the multiplicative inverse of 7 modulo 8. Now this is actually a kind of accident, okay? So you might actually, this table may give you some kind of illusion that the multiplicative inverse of a number is the number of itself. That's generally not true, but only true for Z8. For Z8, okay. Now, if we talk about any actually set like a Z10, Z20, Z100, now that's not always the case. The multiplicative inverse modulo n is not necessarily the same as the number itself. Okay, so that's the accident. 0, 1, 1, 3, 3, 5, 5, 7, 7. That's accident. Okay. Okay, just like any arithmeticals, we have the properties of modular arithmeticals. So when we actually define these arithmeticals, we are talking about the Zn, okay, which is the set of all the integers from 0 to n minus 1. Okay. So here are the properties. The first one is the commutative law, which says w plus x mod n is the same as x plus w mod n. So you can switch the order when you do the addition. And the same thing for the multiplication mod n. Okay, w times x mod n is the same as x times w mod n. Now this is an associative law which also apply, So that means this is generally true with or without mod n, right? In a generally like when we say w plus x is the same as x plus w, this is generally true for the general arithmetical. But for mod n operation, that's still true. And the same thing with associative law. Okay, so x plus x, w plus x parenthesis plus y. So that means when we do this plus first, or when we do the second plus first, now we got the same result. So this is under mod n. And same thing for the multiplication. So it doesn't matter which order we're going to perform. We can multiply w and x first, or we can multiply x and y first. Doesn't make any difference. Now, this is actually the mod operation, but this is also generally true for the operation without mod n. Now, here's the distributive law. Distributive law also true. So w times parenthesis x plus y is the same as w times x plus w times y. So that's a distributive law. Okay. And here's the identities. So that means when 0 plus w, that 0 is the actually element 0. 0 plus w mod n is the same as w mod n. And 1 times w mod n is w mod n. So this is generally true, right? So 0 plus w is w. 1 times w is also w. That's generally true without mod, right? So with or without mod n, this property is also true. And the additive inverse, we always say additive inverse minus w. For each w, there exists a z such that the w plus z is congruent to 0 mod n. So that means for each w which belongs to Zn, there's always an additive inverse, which is also belongs to Zn. Okay, so now we have all these properties for modular arithmetical, and then we can apply this modular arithmetical in one of our computer science application, the network security, and in particular we use we apply to one of the encryption algorithm called RSA. Okay, we're going to talk about this in modular 9C, in the third part of the modular 9. Thank you.